One of the trickier analogies between rotational motion and translational motion is the mass. In translational motion, objects have inertia. If they are moving, they want to stay moving, and if they are stationary, then they want to stay stationary, unless some unbalanced force is applied to them. If a force is applied, then the magnitude of the acceleration depends on the mass. The larger the mass, the smaller the acceleration, and the smaller the mass, the greater the acceleration. So we can say that the mass is the resistance or the inertia that an object has to being accelerated. So in rotational motion, an object also has a rotational inertia, and this is called the moment of inertia, and it's labeled by an I. If a force with a perpendicular component to the radius is applied, it will cause the object to change its angular velocity. This force can induce a rotation called a torque, and we'll discuss that at length in a little bit. For now, we want to know what is a moment of inertia. To see where the moment of inertia comes from, let's consider the kinetic energy of a rotating object. Here we have two masses rotating around the center with masses of m1 and m2 with radii of r1 and r2 and velocities of v1 and v2. So the rotational kinetic energy will be 1/2 m1 v1 squared plus 1/2 m2 v2 squared, where all of the velocity is perpendicular to the radius. That means that there is only rotational kinetic energy, there's only rotational motion, there is no translational motion. If that is true, then the velocity is equal to the angular velocity times the radius. Then we can rewrite our kinetic energy equation as 1/2 of the mass of 1 times r1 squared times omega squared. And we can add that to 1/2 r2 squared times omega squared. So the point here is that the omega is the same for both, so we can change our rotational kinetic energy formula to 1/2 of mass 1 times radius 1 squared plus mass 2 times radius 2 squared, and then multiply that times omega squared. We can then define the moment of inertia as the sum of the masses of the object times the radii, and that gives us their moment of inertia. If we do this substitution, the rotational kinetic energy is now 1/2 times the moment of inertia times the omega squared. So notice the point here is that this is exactly the same form as the kinetic energy, only now I is our analog for mass for rotational motion. To calculate the moment of inertia, if you have point particles, you multiply the mass of the objects by their radius squared, the distance between them, and the axis of rotation. Notice that if two things have the same mass, but one has a larger radius, then the moment of inertia will be larger. That's why if you have, say, a ring, something like a bicycle wheel, it will have a larger moment of inertia than a ball with the same mass. You can test this by rolling both down a hill. What you'll find is that the ball will roll down the hill faster because it has a lower moment of inertia, even though the two have exactly the same mass. Notice that the radius is the distance from the axis of rotation to the mass that we're interested in. And so to get the total moment of inertia, you have to take all of the individual masses and sum them up. So we have this sigma, this thing that looks Greek letter E. That means that we're summing up all of the masses and their radii, squaring their radii, and adding them all together. Okay, so now we have an example to do. So we have an object that is basically four masses that are in the shape of a square, and so each of the masses takes on the corner of the square. What we'd like to know is we'd like to know what the moment of inertia is for the object when it rotates through the center and when it rotates through one side of the square. Let's start with a case where the square rotates through the center of the two sides of the square. So we'll make the two sides of the square 2r. So that means the distance from the axis of rotation and the balls are 1r for all four of the balls. The moment of inertia for one ball will be the mass times the radius, which is just r here, since the distance between the two balls is 2r. and so that becomes r squared. So the moment of the inertia for one ball is m times the radius squared. So all of the balls have the same mass and the same radius, so we can just add them all up to get a moment of inertia of 4mr squared. Right? Each one's mr squared, so we have 4 balls. It adds up to 4mr squared. Now let's look at the case where the rotational axis is through 2 of the balls. Notice the shape and the mass are exactly the same as the first case. The only thing that has changed is where the axis of rotation is. So if we put the axis of rotation through the 2 balls on the left, their radius is now 0, so their portion of the moment of inertia is also 0. On the other hand, our other 2 masses have a mass of m, and their radius is now 2r, twice the distance from the axis of rotation as before. The moment of inertia is the sum of mr squared, so the moment of inertia of one ball is the mass times the radius squared. So be careful here, the radius is 2r, so the radius squared is 2r squared, which is equal to 4r squared. So that means that there are 2 balls at this distance, so if we add them together, we get a moment of inertia of 8mr squared. Notice that the moment of inertia is smaller when the masses are closer to the center of rotation, and the moment of inertia is larger when they're further from the axis of rotation. Okay, so you guys have a problem kind of like this to do, but with a different shape, and a conceptual question about the moment of inertia. Alright, that's it for the so-called Monday class. Good luck and take care of yourselves.